Example 2. So in example 2, this is a complex variant on the chain rule with 3 terms, but only one term is chain rule. So identification is a key for this topic. Don't forget that, making the right identifications. This term here is the chain rule term. This term and this term are just polynomials to differentiate. So they should be fairly trivial. So if I was going to derive this, remember it says determine the gradient, which means I need the gradient function. At x equals 1 means I need the gradient function, and then I substitute in x equals 1. And that will give me the gradient at x equals 1. So that's the point of this. And I'm going to go through this process now. Y equals this. So that means that dy dx will be equal to something minus 9x squared, and the 7 goes to 0. So we're happy with that. That's something there, though, I need to work out. And I'm going to replace that something box with dy du times du dx. So that's our chain rule. It's a chain rule question. And I'm going to write down over here that y is equal to u to the power of 10, and u is equal to 2x squared plus 1 over x. So I've done that substitution. Hopefully through your practice, you're now used to taking that substitution and being clever about your choices. If you're happy with the chain rule, incidentally, a fair chunk of next term is going to be chain rule of exponential logs and periodic functions. And the good news is that actually they're not that much harder. In fact, some would say this is the harder bit. So that's good for you. I'm going to write down that u is now equal to 2x squared plus x to the power of negative 1. So until we get to the quotient rule early next week, if you see a fraction, you're going to write it as something to the power of negative 1 or negative 2 or negative 3 or something. And that means that du dx is equal to 4x to the power of 1, which is just 4x, minus x to the power of negative 2. So I've brought that negative 1 out the front, which makes minus, and it's a 1, so I don't need to write the 1 there, and drop the negative 1 to a negative 2. And I've done that, so I've done some simplification in the same step. And if you don't quite get what I've done in that one step, take some time, you'll get there, but that means you might have to do an interim step in your working, at least for now. But again, if you go through and do, and I hate to say this because maths isn't always like this, but some things, you go and do 20 questions like this, then you won't need that interim step and it'll be easy. Sometimes with some math things, you just got to go and do 20 questions. That's just what it is. So there's my du dx. Y is equal to u to the power of 10, so dy du is equal to 10 u to the power of 9. And now I can go back over here because I know my dy du and I know my du dx. So I've got 10 u to the power of 9 times 4x minus, see this here, I'm going to write it back in fractional form, 1 over x squared minus 9x squared. And I'm going to bring my singular term out the front, so it becomes 10 4x minus 1 over x squared. So when I say my singular term, there's no power on that one. So I'm going to bring that out the front. Whereas the other one, which is my u, remembering that u is 2x squared minus 1 over x, is to the power of 9. So I'm going to put that at the back because it has a higher power. So that's just, you wouldn't lose a mark for not doing that. But that's standard notation, minus 9x squared. And that's my differential. Now, we don't have, and this is where some people go, done, and move on. We're not actually quite done yet. It's asking us to find the gradient at x equals 1. So now I just have to do that last little bit. I'll say at x equals 1, dy dx is equal to 10, 4 times, you don't need these brackets, but a lot of people use them just to denote where they've substituted in. 2 times 1 squared minus 1 over 1 minus 9 times 1 squared. And this is equal to 10 times, inside the first bracket, I get 4 minus 1 over 1, which is just 4 minus 1, which is 3. Inside the second bracket, I get 2 minus 1, which is 1. And at the end, I've got minus 9. So that's 30 minus 9, which is 21. And again, you might get to here and just throw it in your calculator. And that's fine. You've seen plenty of examples where I've gone, I can't be bothered picking up a calculator and then made a numerical mistake that somebody else has had to tell me about. So obviously throw it in your calculator only if you want to. Any questions on that? I did. I did. Thank you, Flynn. So that's a 9. And the good news is that 1 to the power of 9 is just 1. So it doesn't change my answer. It would have been disappointing if it changed my answer. I would have had to log stuff out. But good point. And actually, realistically, you might get lucky in an internal school-based exam, and I might be marking it, just miss that. But that might lose you half a mark or a mark in the external exam. So it's a really good point to raise. So I may have just lost half a mark. So that's example 2. So here's my final summary on a chain rule. Chain rule, this is a little bit more informal. The chain rule is used in situations where you have a function inside another function. For polynomials, it looks exactly like all the examples you're doing. There's brackets around something complicated with a power on the outside. That's going to be your chain rule type question, and you'll see some IEs here. The chain rule also, there's another way, the chain rule and you'll see this is my feelings on this shortcut. It just stresses me out just a little bit because everybody wants to use a shortcut and then 50% of people make mistakes because they use the shortcut when they shouldn't. So just make sure that you're getting the questions right with the shortcut before you use them in the assessment. That's hugely important. So it's by observation, and here's my first example of it. So if y equals x cubed plus 3 to the power of 10, this is an obvious chain rule question where this function is inside the power of 10 function. Now, we would normally say that y dash is equal to dy du times du dx, but you could just say y dash is equal to, well, we take that whole thing and just imagine it's something to the power of 10, and it becomes 10 times that something to the power of 9 multiplied by the derivative of the something. Now, if you're going to do chain rule by observation, you really should still show one line of working. That's my other concern with this. People show a complete lack of working, which can detriment their marks. This is a good line of working. So you're showing that you're deriving it like it's just a standard polynomial, but then you're multiplying by the derivative of the inside function, which in this case, this is just 3x squared. So it becomes 30x squared x cubed plus 3 to the power of 9. So the shortcut is to recognise that dy du is actually just treating it like it's polynomial, and du dx is the derivative of the inside function. And you're welcome to use that, but you will get some negative feedback from me if you make mistakes using the observation method. Cool? Don't be lazy if it's going to cause you loss of marks. And I've written that here in purple. Please, 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 please. That's 4 pleases times 1,000,000. Everybody get it? Cool. So I'm going to use that a couple of times here for you. With these are just the rational ones. Oh yeah, yeah. I'll do question B. So this is exercise 20C, chain rule questions. 20C is just dealing with questions where you've got the cube root of x, which means x is to the power of a third. And then the third comes out the front, and you take 1 off a third. And then you've got to deal with subtracting 1 from a fraction. That's about as hard as this gets. And again, you might be able to do that in your head. That's fine. I do it all the time. I can do it in my head. But if you're going to make a mistake, make sure you do it in your calculator and get the right answer. It could be a tech-free exam, though. So you probably need to know how to do it in your head, or at least do the calculation on paper. So the first, I may as well just do them both. The first one very quickly is y equals x to the power of a third which means that y dash is equal to a third x to the power of a third minus 1, which is a third x to the power of negative 2/3. Now the trick here is to recognise that you have to write your answer back as a rational function if it's given to you as a rational function. We will expect that. So then you have to take this back to be 1/3 times 1 over the cube root of x squared. So the 1 over comes from the fact that it's negative 2/3. The cube root comes from the 3 in the denominator. The squared comes from the 2 in the numerator. So you've got to know your index law so you can put it back in this form. And then I can combine those. Yeah. So if it wasn't, then it wouldn't be 1 over. It'd just be, yeah. And so I'm out of space, but I would probably write that in conclusion as 3 and that combined on the bottom. So you can see the cube root of x derived becomes something quite complex. B, which I'll do by observation, is equal to 3 times x squared plus the square root of x to the power of 2. I've just done that thing, bring the power at the front, decrease the power by 1, leave the function inside the same. But I have to multiply that by the derivative. And this is differentiation as a verb, which I know sounds weird, but this is the doing thing. If I want to derive something, I say d dx that thing. Whereas dy dx is the noun, it's the name for the derivative. D dx is the do the derivative. So d dx of x squared plus x to the power of a half, I may as well make that change now, and that's equal to 3 x squared plus the square root of x squared times by 2x plus a half x to the power of negative a half. And then I'll bring it all together. 3, this thing, because it's not squared, it's just power of 1. I'm going to put that first, is 2x plus 1 over 2 square root x. So I've just put that into one thing, and then I'll put the more complicated term second. And it's more complicated because it's raised to a power of 2. And that's the final answer. So they get pretty tricky, you can see. But then again, it's hugely procedural. So you just got to do this step, do this step, do this step. Make sure you don't make any mistakes along the way. Can I just say one other thing here? That's a hugely common question, or part of a question. Square root of something is massively common. X to the power of a half, when you derive it, goes to that. Goes to 1 over the square root of x, and you end up with a factor of 2 on the bottom. So you might see that a lot. Get used to that. You still have to show you're working, but you know what it is. So that's the first part. That's just covering our basis from last time. If I can teach you some product rule stuff today, I know I'm not probably going to give you a great deal of time, then we're up to date. Next week, we'll have heaps of time. Okay? So hopefully you're happy with the fact that I gave you loads of time early this week, inadvertently. So the product rule is not like the chain rule, because the chain rule is for function of a function. The product rule is for when you have two functions multiplied together. And so you've learnt the product. You probably learnt the product in year 5, 6, 7, 8. You use that term product. If the word product in maths means multiply. The product of two numbers is those two numbers multiplied together. So that's why the product rule is for two functions multiplied together. So in this case, in terms of identification, this is two functions multiplied together, whereas this is only one function, but it's got a function on the inside. So in terms of identification, that's a chain rule question. Now, I promise you, this is the biggest issue, is that people get the identification wrong, and I get an exam back, and they've done all the product rule questions using the chain rule, and all the chain rule questions using the product rule, and lose 25 marks out of 60. And it's massively detrimental, and it happens every year. So one of the things you can do, and the textbook doesn't do it well, because the textbook does this thing, it goes, here's exercise 20B. It's all chain rule. here's exercise 20D. It's all product rule, and you don't get a chance to mix them up. So one of the things that you can do is go into the chapter review. Don't do the questions. Just find a big exercise of mixed questions, and then just go through and write P and C next to all the ones that are product and chain rule. Get practice at identifying them. Don't worry about doing them, because doing them is just procedural. But to do them well, you have to identify them correctly, and it just causes me a lot of headaches, and I want you to get it right. Identification is key, and no one spends enough time on identification. So make sure you're getting them right. When you're doing exercise 20 here, you'll be practicing the actual procedure. You'll know it's product rule every time. You'll practice the procedure. Then practice the identification. The product rule is a little arbitrary in cases with just polynomials. Usually there's a chain rule inside. Yeah, so the product rule becomes massive next term when we combine it with periodic functions and stuff like that. For polynomials, it's quite arbitrary. But anyway, here's the more mathematical variant of the product rule. This is what you'll probably see. And I can't remember what's on the formula sheet again, but we can have a look in a second, or maybe Reggie can have a look for me. So if we have a product rule question, the function is equal to some function times another function. And the derivative is equal to u dash x times v, and then v dash of x times u. So basically you just divide the first times the second, plus divide the second times the first. And it looks better like this. Y equals uv, y dash equals u dash v plus v dash u. Okay, and there's a plus in between, so the order doesn't matter. Just remember you've got to derive one times the other and derive the other times the first and add them together, and you're on. Reggie, what's your conclusion on product rule on the formula sheet? The first one. I think that's why I put it on there like that. So that's the one you might see on the formula sheet, but you know what? It looks like the second one in that you've got u dash v, v dash u. If you just get rid of all those bracket x's, you've got this second one here. So, I mean, generally speaking, most people, when you say product rule to somebody, they'll say, oh, that u dash v plus v dash u thing. So here it is. Example 4. Without expanding, determine the derivative in each case. I'll leave that bit up there so if you're copying it down. So the derivative in the first case, this is how we do the product rule. This is why it's arbitrary as well, because you could just expand that. That's what makes it a little bit arbitrary. I'm going to let u equal 3x squared plus 2x, which means that u dash is equal to 6x plus 2. And I'm going to let v equal 2x plus 7, which means that v dash is equal to 2. And then my product rule is going to look a little bit like a times. I'm going to cross multiply the v dash with the u and the u dash with the v, and the product is multiplied. So you get a bit of a times in there anyway. It works really nicely. And that gives us y equals u dash v plus v dash u, which is 6x plus 2 times by 2x plus 7 plus v dash, which is 2 times 3x squared plus 2x. Now, I've made this little note down here. Not massively important there, but I'm going to start this habit with you. Every time you do the product rule, look to factorize as much as you can. We expect you to factorize as much as possible because we expect you to simplify. And simplify means factorize. It doesn't mean expand. You might look at that and be tempted to expand it all out. That's not simplifying, because we're better off knowing the factors, because that gives us a chance to cancel factors out. So in this case, if I factorize this, you'll notice that in the first term, which is the first two brackets, I can take a 2 out of the 6x plus 2, which gives me 3x plus 1, 2x plus 7, there's no common factor there. In the second one, I can take an x out of that bracket, which gives me 2x times 3x plus 2. And then you'll note that I can take a factor of 2 out of the whole thing. 2 times 3x plus 1, 2x plus 7, plus x times 3x plus 2. And I know I promise. Most of you are thinking, well, that was a waste of time, and it kind of was for this question, but it's not for all questions. So I need you to learn to factorise and get used to just doing it and looking for it, because when the questions get more difficult, you will find what will happen is you'll take a bunch of factors out here and you'll be left with just 3x and 2x minus 7, and all of a sudden things will simplify. That's what we're looking for, those opportunities. What have I got? I got B, and then I'm stopping. Here's question B, because I know I've seen all your eyes diverting to the clock. I see it. I know what's going on. Here's my second one. I can move the clock above my head if that helps. That'll be, but then you wouldn't be able to see. I'll sort it again now. Cool. U equals x squared. U dash, that's wrong. U equals x to the power 7. U dash equals 7x to the power 6. V equals 2x squared plus 1 to the power of 6. V dash equals. Now, sometimes these second term will be a really complex chain rule question. In this case, I'm going to do it by observation. It's not that complex, but it is a chain rule. Inside function, power 6. So you could do it using the dy du dx thing. I'm going to do it using this. 6 times 2x squared plus 1 to the power 5 times by the derivative of the inside function. Hopefully you all agree that the inside function is 4x. The derivative of the inside function is 4x, which gives us 24x 2x squared plus 1 to the power of 5. Questions on that? That's a shortcut observation. I'm pretty confident I didn't make a mistake. So if you're not making mistakes, that's good. And therefore, f dash of x equals u dash v dash u 7x to the power of 6 times 2x squared plus 1 to the power of 6 plus 24x 2x squared plus 1 to the power of 5 times x to the power of 7. And that's equal to 7x to the power of 6, 2x squared plus 1 to the power of 6, plus 24x to the power of 8, 2x squared plus 1 to the power of 5. If this was a question in your exam, you're currently sitting on 3 out of 4. 3 marks out of 4. There will always be a mark associated where it's possible to do some decent factorising for the factorising. So now we're going to do that factorising bit. I can't factorise this bracket or this bracket, so the individual term factorisation is already done. There's nothing more I can do there. But I've got an x to the power of 6 here, and I've got an x to the power of 8. That means that I can take out x to the power of 6, which leaves me no x's there, and it leaves me 2 there. The 7 and the 24, there's no common factors between 7 and 24, but I've also got 2x squared plus 1 to the power of 6 here. I've got 2x squared plus 1 to the power of 5 here. I've got 5 of them there, 6 of them there. So I can take 5 of them out, 2x squared plus 1 to the power of 5. And that leaves me with none here. And it leaves me with 1 there. So what have I got left? I've got a 7, and I've got 2x squared plus 1. And in the second term, I've got plus 24x squared. Now, have a look at this and go, that is definitely worth expanding this bracket and simplifying, because it's going to happen. Okay, x to the power of 6, 2x squared plus 1 to the power of 5, and I've got 14x squared plus 7 plus 24x squared, and happily that becomes x to the power of 6, 2x squared plus 1 to the power of 5, 38, that took me longer than it should have, plus 7. That. And be careful, because sometimes you might then be able to refactorise further there. And my last thing I'm going to say to you is the most common place this will be handy, and think about this, is if you actually want to find where the gradient is 0. So if you want to find at what points in this function is the gradient 0, you let the gradient equal 0. How would we solve this when it's equal to 0? That again? There's something, null factor theorem. So if this thing equals 0, one of those things must be 0 for this whole thing to equal 0. And it only works when it's in this form. This is 3 factors multiplied together. Up here, or here, we've got 2 separate terms. We can't use a null factor theorem when there's 2 separate terms. But by factorising, we've brought it down to 3 products rather than 2 terms, which means we could solve equals 0. If you want to formulate gradient 0, that means that it's flat. Gradient 0 when it's flat, so you can find peaks and troughs, or you can find minimums and maximums, turning points, and they're really important functions. Anyway, that's 20E, which I'm pretty confident you can do. The questions are pretty much like that. That's product rule. Chain rule, practice them. Once you are confident with product and chain rule, then practice identification. I'm going to stop this there.